In the last video, we talked about how to find an angle that was not one of our normal reference angles. It wasn't a pi over 6 or pi over 4 or pi over 3, and we looked at what they would have to do is give you something like, sine of pi over 9 equals, and they'd give you that proportion of sides. Well, there's another way that we can find other angles, despite the fact that they don't look as though they're one of our reference angles. And this is a classic example. When you think about our reference angles, we have pi over 4, pi over 6, and pi over 8. So just to keep that in mind as we're doing this, I'm going to use a little thought bubble here. Pi over 6, pi over 4, and pi over 3. We also, of course, have pi over 2 and, any of the quadrants that involve all this stuff, as well as your pi's, right? So when we're looking at something like 5 pi over 12, and we notice that it doesn't say equal to a ratio of sides, maybe your initial thought is, whoa, we can't do that. But you can, because we can use the reference angles that we do know. More specifically, we can use these identities, which is the sum of two angles here, sine of a plus b, or if we're talking about cosine, the cosine of a plus b. And this identity that we find here is identified with sine, cosine, plus cosine, sine. And then the cosine one is cosine, cosine, sine, sine. Can you hear the rhythm to that? Sine, cosine, cosine, sine, cosine, cosine, sine, 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 cosine, cosine, sine, cosine, cosine, sine, 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 cosine, cosine, sine, cosine, cosine, sine, sine. If there's something gets stuck in your brain, that's good. It helps us remember those. Now, the truth be told, these are given to you on the CLEP exam as part of the introduction to it, where the directions are located. And if I'm not mistaken, there's even like a little side thing that you can bring up, but it's nestled amongst a whole bunch of writing. And honestly, it just makes it easier if you know it. So it's that simple: sine, cosine, cosine, sine, cosine, cosine, sine, 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 cosine, cosine, sine, cosine, cosine, sine, sine. Get your own little song going. All right, but all's well and good if you can know those, but if you don't know how to use them, then that's another issue, right? So first of all, we need to recognize that we need to be able to write 5 pi over 12 as a sum of two angles, and not just any two angles, but two angles in which we know. So your approach to this needs to be like so. You are going to put your reference angles with that same denominator, okay? So put reference angles with same denominator. And so in our case here, we're going to look at pi over 6, pi over 4, pi over 3. And if we need to, we'll go to the pi over 2, and you'll see what I mean in just a minute. I'm going to write these all with having a denominator of 12. Okay? And so this first one would be 2 pi over 12. The next one would be 3 pi over 12. And the last would be 4 pi over 12. Now, second step, right? Second thing. You now need to determine which two angles will add will give a sum of what you need. Now, I will tell you that there may be times that you have to go in the other quadrants. And so we'll look at those examples more in class, but understand that there will be times in which you might have to go into the second, the third, and the fourth quadrants, depending on really where it falls helps. If you're like, well, how do I know where 5 pi over 12 falls? Think of 6 over 12 would make that 1/2, and so it's got to be in the first quadrant. So that means to me that I'm going to use the first quadrant reference angles. Hopefully that makes sense to you. And again, I hope that you can see that we have 2 pi over 12 and 3 pi over 12. So what does that mean? All right, so that says to me that I am going to now do the equation sine of a plus b, but I'm going to use pi over 6 plus pi over 4, because I know that when I add those two angles together, it's going to give me 5 pi over 12. And so my third step is to now use the identity with those angles. Okay, so what does that look like? That means I'm going to do sine of that, right? Because this is deemed as A, this is deemed as B. So pi over 6 cosine of B plus cosine of A sine of B. You'll notice the angles in both sine and cosine formulas here go A, B, A, B. It's just one goes sine, cosine, cosine, sine. The other one will do both the cosines together and both the sines together. All right, let's keep going. So the sine of pi over 6. Using your unit circle, this should be relatively easy. At least I hope it is. When you look at pi over 6, what is the sine? That, of course, is our y value. That's 1/2. And cosine of pi over 4 is root 2 over 2. Cosine of pi over 6 is root 3 over 2. And sine of pi over 4 is root 2 over 2. And then, of course, I'm not, and ran out of room here on the bottom, but the last thing is to simplify this. So I have root 2 over 4 plus root 6 over 4. Since they are not the same numerator, or same radical, I can't combine them. So this is my final answer. You could write it as one denominator. Sorry, root 2 plus root 6 all over 4 means exactly the same thing. I'll take either. All right, let's do cosine. Well, we already have determined, same process, put reference angles with the same denominator, which we already have here above, right? Second step is determine which two angles will give us the sum of what I need. I already know that. So how it uses with cosine would be the cosine of pi over 6 plus pi over 4. And that would mean the cosine of pi over 6 cosine pi over 4 minus the sine of pi over 6 sine of pi over 4. And so similar to what we did already, the cosine of pi over 6 is root 3 over 2. And then we have root 2 over 2 minus the sine of pi over 6 and the sine of pi over 4. And so I would get the square root of 6 minus the square root of 2 all over 4. And that would be the cosine answer. Along with finding theta, this is obviously with the ones that are not reference angles. We could also have finding theta that looks like this, where we have solve for theta, and then it just gives us sine 2 theta equals 1/2, and cosine 2 theta equals 1. The first thing I want to just tell you is we did this. Chapter 3, no different. So use this as a review, okay? Use this as an opportunity to review, and I'm going to do these two examples for you so that you can see it once again. Bottom line is we want to get to theta. So you're going to peel away the layers just like you would any other equation. You want to basically get rid of the sign. And of course, to get rid of the sign, you're asking yourself, either you want to do the inverse of both sides. So some people, you might think, oh, I'm going to do the inverse of sine. And that is absolutely great. Those signs would cancel out. I'd be left with 2 theta equals. And so what this is saying to you is, when does sine equal 1/2? When does y on your unit circle equal 1/2? And because it's on your unit circle, this is a beautiful thing. I mean, you're really just looking at, hey, sine is our y value, so 1/2. And so you're like, oh, it's 1/2, so there should be 2 spots on a circle, right? Because you're thinking of that unit circle. There should be 2 spots to where it equals 1/2. Should be kind of obvious to you. And so we should get pi over 6, right? And 5 pi over 6. Those are the 2 that we have. Make sense? Now, what we would do here then is to solve for 2 theta, we would then divide by 2. But here's what I want to remind you of, okay? So we find the angles that it works for. We know in the first and the second quadrant, that's where sine's positive. But another thing that helped us with this 2 theta reminds us that, hey, that's the frequency. So that really means that sine is happening 2 times. Okay, it means we're kind of going around the circle 2 times, so to speak. And so what we did back in chapter 3 was we listed all of the quadrants, and we went back around again, right? In other words, we go around 2 times, and then we solve for theta. So this would be pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. Does this ring a bell to all of you? I hope so. Let's try another one. All right, when does cosine equal 1? So almost like covering this 2 theta up for a moment and saying, when does cosine equal 1? Just think of when that happens. And of course that happens, and I'm going to write 2 theta equals, that happens at 0, and it happens at 2 pi. But again, that 2 theta tells me that how many times around am I going to go? I'm going to go around 2 times. And so I'm going to say, oh, that means I also need 4 pi. And then to solve theta, divide by 2. 0 divided by 2 is 0. Pi, 2 pi. And there would be the answer there. So solving for theta is 2 different things. This, of course, we have the equation to which we can solve, and we can actually think about when does sine equal that proportion, and we can go right at it, making sure we go as many times around as the frequency dictates, and we divide by that number that's in front of theta. We also have the kinds of solving for theta where, hey, whoa, we have to figure out, and it's not theta in this one. This is just giving you an angle that's not one of our reference angles. So 2 different things that we did. And we're going to look more in depth in the next video about identities and all of the identities. So this just kind of gives us a foundation for those identities. And again, just more of an extension on finding theta.